So, good evening, everybody. Good evening, everybody, to this Saturday manufacturing talk of the 8th May. This is our 9th in the series of the Saturday manufacturing talks, which is being organized by the Center for Excellence in Advanced Manufacturing Technology. Myself, I am Professor C.S. Kumar, faculty of the Mechanical Engineering Department at IIT Kharagpur. I also am holding the current administrative position as the head of the Rajendra Mishra School of Engineering Entrepreneurship here at IIT Kharagpur. It is my pleasure to have Professor Kailash Kapur, a professor of the Industrial and Systems Engineering at University of Washington, Seattle, in US. Just to remind all viewers and to those who have come in afresh, who may have joined in this series afresh, the Center for Advanced Manufacturing Technology has been set up under a program which has been developed as a between IIT Kharagpur and the Department of Heavy Industries in the Government of India, which encouraged us to have a strong industry academia collaboration. And there are many industries working with the faculty of IIT Kharagpur who have industry-specific projects to solve some of the challenging problems wherein the Indian Institute of Technology, the knowledge base and the faculty expertise can be used in tackling some of the upcoming problems wherein they are not yet ready to accept it, but they are willing to try first with the academia. And in this course of many projects and the journey that has taken place, there was a short video which was played before this. There have been many events which have taken place, inclusive of having training events. In addition to all of this, we have had this Saturday manufacturing talks which have been launched, wherein we have experts from the Indian academia and the international academia, particularly those who are alumni of this institute or have been associated with this institute, have been requested and have consented to give talks on interesting topics of various kind. So today we have Professor Kailash Kapur from the Industrial and Systems Engineering Department of University of Seattle. Dr. Kapur is the Director of Industrial Engineering at the University of Washington from 1993 to 1999. He was a professor and the Director of School of Engineering at the University of Oklahoma from 1989 to 1992, and a professor in the Department of Industrial and Manufacturing Engineering at the Wayne State University, Detroit, Michigan from 1970 to 1989. He has worked with General Motors Research Laboratory and was a visiting scholar for the Ford Motors. He has done training and consulting over 50 companies, both national and international. He received his PhD degree in the Industrial and Engineering and Operations Research from the University of California, Berkeley. And he is an alumnus of this institute as an MTech in the early 60s. He has also been a visiting professor. He has had visiting professor appointments in the University of Maryland at College Park, Beihang University, In China, Norwegian University of Science and Technology, Trondheim, and Hong Kong University of Science and Technology in HKUST. He has co-authored 3 books in reliability and engineering design and reliability engineering, both published from John Wiley. He received the Alan Chop Technical Advancement Award from the Reliability Division and Craig Award from the Automotive Division of American Society of Quality. He is a fellow of the American Society for Quality, a fellow of the Institute of Industrial Engineers, and a registered professional engineer. With such a strong background in reliability engineering and in industrial and operations research, I will now request Professor Kailash Kapur to talk about quality control in manufacturing, past, present, and the future, which he has kindly consented to do so. Over to you, Professor Kailash.
Thank you very much. It's my pleasure to be here today and my honor to give you some ideas about the broader field of quality and quality in manufacturing, and then share with you some of the philosophical ideas. Let me see if I can share the. Are you able to see this slide? Hello?
Yes, we can. Yes, we
You can see. Thank you. Just wanted to make sure. So I've been teaching in the United States since 1969, and there is a picture of our campus. You can see there's a big fountain in the center and the mountain that we call fountain and the mountain on our campus. And this is a view of the city of Seattle. And today I'll give you some ideas about quality control in manufacturing and look at the evolution of the word quality, and then what happened in the past, what is happening now, and then what we may be doing in the future. So a lot of my presentation is a little more philosophical because I focus a lot on understanding the meaning of the word. So we'll talk about a brief history, definitions, what are some of the principles, what beliefs all of us have, philosophies for quality in manufacturing. And we try to extend and enhance the quality discipline to the next level. The question is quality only in manufacturing or quality at every level in our life? And then what are some of the traditional barriers to improving quality related thinking? So we can look at some barriers. And one of the big barrier has been is what does quality mean? And then every decade people come up with very different ideas what quality is, and then it creates a lot of conflicts in the society and in the methods. So a lot of quality evolution was based on inspections. Because if you look at the word quality control in a dictionary, it will talk about, oh, you like to inspect, audit, you evaluate what somebody else is doing. So we'll talk that we want to do less of these things. And why we want to do that, we can develop some ideas, some philosophies. So we'll talk more about holistic or systems thinking so that the methods, philosophies, technologies related to quality can be integrated and effectively implemented with broader impact on quality of not just manufactured products, but also about quality of life. So focus of presentation is more on ideals, not what we have been doing, but what we should do and what is the hierarchy of understanding of cause and effect. So when we use the word quality, I'll try to literally look at the meaning of the word and then integrate and synthesize many qualities. And then how we can go back or go forward from doing feedback, inspection, which is outcome focused, to diagnostics, to prognostics, to the idea of feed forward control, the hierarchy of proactive management. And I will draw a lot from biological systems in order to promote basic ideas of quality, because there's so much wisdom there, and over billions of years of evolution, these biological systems understand how to survive and how to be reliable, how to be resilient, how to be robust. And we can learn a lot from those systems. And then we can implement those ideas in quality control in manufacturing. And briefly, we'll talk about some of the limitations of traditional binary thinking. In quality, people always talk about good, bad, win, lose, success, failure. But we'll talk about that there are infinite possible states of the system. So you could model at least multi-state, continuous. You can also use concepts of fuzzy sets or logic or thinking. And then quality, like any engineering is based on science and mathematics. So we may briefly talk about even limitations of science and mathematics. So let's look at a brief history of quality. We say, what is quality? It says we use this simple word every day, but nobody knows how to define it. If you talk to a vice president of quality in an organization, I say, you're the vice president. What does the word quality mean? So they'll give you one definition. You talk to another person, they will give you a different definition. And this definition, you'll find a lot of evolution, past and present, has been based on how people have changed the definition of quality. And this has been a barrier to improving quality and productivity in many countries, national, United States, and international. So we can go back, like you can talk about Big Bang, but maybe 13 billion years ago. But even if you go back for 2,400 years back, Plato talked a lot about what something is. So he created this word, a whatness or of what kindness. So he was able to look at this word quality in a very different way. So we should be able to then look at this word and then say how this word has evolved. And my definitions would be more based on historical perspective. And we'll try to answer what is quality, why, when, where, how much, and on and on. So you can see we're going back to this word almost 2,400 years ago. You can see the confusion is even based in the United States. If you look at American Society for Quality, even beginning of this century, they had a cover article. It says, what is quality? And here is the society. They say, we don't know what quality is. So we can go to 8 experts. And maybe these experts will tell us what is quality. So in this feature, they talked about Crosby and Deming and Feigenbaum and Dr. Taguchi. And everyone has a different definition for it. So then when audience reads it, they're very confused. They say, what are they doing? So this is almost my analogy that this beast, very, very complex, and we are blind men, women, and we are just looking at one part of the elephant, and nobody understands the bigger picture. And the main issue has been is how you articulate that word how you define it, how you measure it, how you evaluate it, where you think about of that word. So in real life, we know there is an operational definition. You could say in a professional society, they have a definition. There is a dictionary definition. So we can, best idea is always is to start with the dictionary. So like many words in English language, the roots are Latin. So if you look at the Latin word quality, it says quality comes from the word qualis. Qualis meaning how constituted and signifies such as the thing really is. So modern dictionaries may define quality as the essential character of something, nature, an inherent characteristic or attribute. So in my presentation, we'll more look at quality as a characteristic, as an attribute of the system. This way, a system has infinite qualities. It's not just one quality. So rather than talking about infinite qualities, sometimes we just use the word ilities. There's so many ilities like reliability, maintainability, resilience, sustainability, and many qualities. And then there is a hierarchical perspective. How you evaluate quality is typically a traditional definition of quality. When we say, oh, this is a quality product, people are more focusing on evaluation of quality, a metric of degree of a good. So we talk about hierarchical definitions of quality. So this is what we deal with. Uh, is there some issue with quality with the voice? Okay, so we'll talk about systems thinking and hierarchical interpretation of quality at the higher level, next level. There are many levels for a system. And many times then in 50, 60 years ago, people start talking about, how does quality, goodness of a product evaluation impacts people, the user, the customer. And then people say, oh, there are many qualities of a system, like technological qualities. If material has the best hardness, it is the hardest material, doesn't mean it is best from the viewpoint of the customer. So typically, we are always looking at designing something based on technological characteristics. We talk about objective as well as subjective, like how people value a product. So what is taste, beauty, delight, they are different from person to person. How qualities change over time, like reliability, ethical issues. Many companies, they'll say, oh, we have 2 issues or 3 issues. We want to improve quality, but we want to decrease cost. You can see that in this perspective is wrong because cost is one of the qualities of a system. You can always increase hardness, cost will go up. Doesn't mean the customer is happy. So people forget, they separate quality, they localize it more in terms of engineering characteristics and not take a holistic approach. They say we want to improve quality, decrease cost, decrease delivery. That doesn't make sense because so that doesn't make sense because if you don't spend a lot of time, I want to turn off the phone. So that doesn't make sense because if you don't develop the product properly, you will have problems in the future. So we can go back to the last century, and one of the first person that had a big impact on quality was Walter Schuhart. From 1891 to 67, he met Prime Minister Nehru in 50. before, so you can Google his bio. So he talked very briefly. He wrote the first book on economic control of quality of a manufactured product. Because one of the key words he has is the word economics, that focus on cost. What is a cost-effective way to manage a quality of a manufactured product? The question was, what was his definition of quality control? So you can see the first idea is how you engineer something. So you use your engineering knowledge and you use what I call as substitute characteristics, and then translate those to the needs and the desires of the customer. And then the second step, that was the foundation of the book, was that how you can manage it so that the variation in quality, it says unit to unit variation, would be very, very arbitrary. So whatever standard you set, then you could say, oh, I can make products within those limits or within those standards. And that is all left to chance. So the basic idea he was able to promote was that if you look at, like I always present this hierarchical approach, that you cannot eliminate defects or claims from the customer unless you change the foundation. We say it is hard to eliminate the top of the pyramid unless a lot of work is done here. If you focus on process variation, process abnormality, then hierarchically you'll be able to minimize the claims from the customer. So then the focus has to be on causation and hierarchical promotion of variation from one level to the next level to the next level. So we have to focus on reducing the abnormalities of the process. In a manufacturing product, and the question is, what is causing the variation? And then people started about the concept of a control charge, and the purpose of a control charge was only to eliminate the special causes. So let me give you briefly some idea what this philosophy is or was, and what are the weaknesses of this philosophy, and whether even we want this philosophy. So the idea is that you have a process, a manufacturing process. You look at the output. When you look at the output, you measure some quality characteristics. So the word quality means that you're looking at hardness, or temperature, or some dimension. And then there is a variation. And then you monitor the variation over time. So if the underlying statistical distribution is changing, then we say, oh, process is not in control. So when they use the word quality control in the context of a control chart, it is more about statistical stability. It has nothing to do with goodness or badness of quality. So if the process is changing, and then you can look at two parameters of the process like mean and variance, then you say, oh, we cannot predict. I don't know what I will give it to the customer. So it is much better to make sure that the process is stable. So the whole notion that something is in control has a very limited definition. It means that the underlying statistical distribution is stable. Then why is this variation? So they call that is as a common or chance cause of variation. And then why there is a mean is changing or variance is changing, they say there are some special or assignable causes. So people in the beginning, more than 100 years ago, thought most of the quality problems are due to special or assignable causes. And if you can assign a cause, they think you have fixed the problem. And then if you can get rid of the assignable causes, then there is no quality problem. So in the beginning, a lot of people thought most of the focus has to be on assignable causes. As we learned more and more then the percentage of causes that were given to assignable kept going down and down and down. And today we think that the main issue is the common causes, how to fundamentally improve the system. This has a very, very limited role if you want to improve the quality. So this has been a big shift. Common means they are part of the system. They are built within the system. And another concept we'll talk about is that you also don't want statistical stability too, because the focus is if I have this distribution, 1 year from today, I still don't want this distribution. I want a different distribution where mean is closer to your target and then the variance is small. So you don't even want stability. Stability means you're stuck and you don't want to be stuck. You want to change and you want to change for the better. So that will be another idea that talks about limitations of control charts and statistical stability. The traditional metric to improve quality, you can see a lot of focus in 1940s and 50s was conformance to specification. General Motors would say, oh, good product is that meets the specification. But then the bigger issue is what is the quality or how good are the specifications? So you can see, and specifications are barrier to improving quality. If I give you these two limits and everything is in between the limits, you say, oh, I cannot improve it any further. So they put barriers to improving quality and productivity. So we'll talk about that the focus has to be on continuous improvement. In this picture here, we say if there is a target, there is always a distribution, variability. It doesn't have to be normal distribution. And more you move away from the target, there is a continuous evaluation. And then you focus on the whole system. So that means when you evaluate quality, you not only look at non-conforming items. We don't use the word defective in books in 70s and 80s because defective is a relative word. So we talk about whether it conforms or doesn't conform. So there is a continuous degradation of the performance of the product, and then you integrate over all values of y, every y characteristic, not just this is as good as this is as good, but you focus on continuous evaluation of the product. So that's where then you can use multi-state or continuum models or fuzzy sets to measure quality. So a lot of new work should be based on a continuous evaluation of quality. So a lot of effort that was done was on process capability indices. And you can see these indices by definition focus on the present mean, estimation of the mean, and the standard deviation of the product, and then focus on the specific. And whole philosophy of Six Sigma was based on this idea. And I think now all of us know that how limiting this thinking is. And this is a big barrier to improving quality and productivity. And philosophically, if you really think and understand the physics or the sciences behind the system, no process is really stable. Everything is always changing. Nothing is statistically stable. And you don't even want it to be statistically stable. But the basic idea is that even if things are not stable, I want to be able to adjust them or manage them. And then the main issue of quality control has to be where is something today, then how to predict where it will be tomorrow, how we can use that idea to make adjustment proactively today to hit the targets in the future. So that is the philosophy that I will try to present to you. And a lot of work that was done in 50s and 60s and 70s was more focused on variability and mostly variability of the output, then people said, oh, output variability is the variabilities of the input. Rather than focusing on the output, you should focus on the input. But every input is an output of the previous process, the previous process, the previous process. So our definition of a customer is anyone that I affect my process, that is the customer. But then you could try to make optimization models and you try to say, oh, how much variability this characteristic should have, and this characteristic have, and this characteristic should have. And then we can try to understand the and then you can make an optimization model. What is the best thing to do? So this used to be very popular, the tolerance optimization, or what we say trade-off or cost-benefit analysis. I know everybody uses cost-benefit analysis, and this is how many companies work. But the challenge with cost-benefit analysis, if you go to a company, any company, and ask them what's the cost of doing something, it's like somebody says, "Oh, eh, I'm going to give a lecture today. So what's the cost of giving this lecture?" It is almost impossible to calculate. Cost at IIT, cost in India, cost in United States, all the life I've spent maybe thinking about these ideas. And then even if you're able to estimate the cost, it's almost impossible to say, talk about benefit. The same thing is true in manufacturing. When we use the word benefit, harder question is benefits to who? Like if I'm giving this presentation, benefits to who? It's like a couple of students at IIT, some people in industry in India, in Africa, in China, in United States. And hardest thing always is benefits for how long. So if you change benefits for who and for how long, if your planning horizon is a 1 month or 1 year, you'll have a very different. So that's why in this presentation, we'll talk about, you know, though people want to do economic analysis, it has tremendous limitations. And it's very important to understand what our belief and value system is. Then the question is, what is a good belief system? What is a good value system? What are some of the underlying principles? So let us review like what we did. So the idea is that this word quality is very, very broad. There are infinite qualities. All of those impact the customer. The language of the customer is very different than the language of the engineer. So that is this word substitute. Many slides in my presentation will just use the word substitute. When I'm looking at hardness or softness of a material, temperature, pressure, they are substitutes in terms of how it impacts the happiness of the customer. So this just talks about most of the quality problems are what we say lost in translation. What the customer wants versus what is delivered to the customer, and what is delivered to the customer changes throughout the life cycle of the product in the organization. So the word substitute, to reinforce, substitute is like we say is the needs of the customer. That is the end. That is what and how I achieve the ends. That's what engineers do. That's what Walter Schuhart talked about. How you use the means to achieve the ends. So this idea became very popular in 60s and 70s and 80s. It started in Japan, and then people start talking about in the United States how to take the needs of the customer and come up with a finished product. So some of the words that were used in Japan was quality evolution. In the United States, we use the word QFD, or quality function in deployment. And people said, oh, like inspection and audit is a form of insurance. If I make 5 bad items out of 100, I could inspect them and take them out, then cost will go up. But that is not assurance. The word assurance is more how to prevent problems from happening. Sure. So that's why in 70s people say, oh, this traditional statistical control or statistical process control, we have to expand it from the word control. You can say control has very limited benefit. So people talked about assurance in a very broader sense, and then people start thinking about how to manage quality in manufacturing, in design, during research and development, and on and on. So that idea of broadening was promoted by Dr. Feigenbaum. He was a professor at Stanford. He understood concepts of systems. So he started promoting the idea of total quality. So you can see even this word has problems. Somebody says, oh, today I'm doing total quality. That means what I was doing yesterday. If I was doing yesterday, I was doing partial quality. That's very demoralizing. But then what will I do in the future? I'll do total of the total. So you can say this was an admission that what everybody was teaching in the universities, writing books, they all had limitations. They were not taking the systems perspective. So that's how in 80s and 90s, the concept of TQM evolved. So you can see how we are evolving slowly and understanding the limitations of what we did in the past. So people say we should focus on a process or a quality process, something that meets the needs of the customer. But if we say, what's the quality of A? It's very, very hard question to answer. It says something is needed, and then we have to say how to prevent the recurrence of the causes of the problem based on learning in the past. Best thing I can do today is to design the means to achieve the ends. So improve the design so that I can prevent it from happening in the future. The only way you can prevent it happening in the future is that if you do something different. And only way you can do something different today is not to make the mistake that you would make yesterday. So this would be a very basic principle of quality that I will try to promote. So this we say traditional versus ideal. Traditional is more outcome focused. Conforming, non-conforming, you could use the word defective or non-defective. And then we give feedback. If you think about feedback, you can say, first I do bad things, and then you tell me I'm doing bad things, and then I correct them. This doesn't make sense. Even if it takes me 1 second to give you feedback, during that second, I've been doing damage. If you think about it, you see, feedback is such a important topic. We teach so much in engineering, but it has its limitations. So we will talk about that how in biology we don't focus too much on feedback in how the life has evolved. So the idea is that if there is a Y output, we all know that Y will change, Y can become non-conforming if A changes or B changes, and so on. So rather than monitoring Y or having a control chart on Y, I should have a control chart on A. And then I can do the same logic in the past. So then once I understand, if I'm an engineer, I have to understand how to design, because that is the word subject. So that means I have to understand this function G, how these variables are transformed to this variable. If I don't understand this function G, I have no right to be an engineer. So then the basic idea is that you more focus on A, B, C, D, and then you go back, then you apply this step again and again and again, and then push quality to the beginning of the life cycle of the product. Dr. Deming had a lot of contributions. He started working, he knew Dr. Walter Schuhart. He talked about the control charts quite a bit. I think so much money was spent, and in retrospect, I could say it was wasted. on applying these statistical thinking when we know they were fundamentally flawed. And then Dr. Deming in 70s and 80s start realizing that the weakness of statistics and those statistics is promoted throughout his life, then he realized the weakness of statistics. So let's very briefly look at the weakness of statistics. So this is like also then Dr. Deming's thought process. So you can see if we look at the time, past, present, and the future, statistics, traditional statistics focuses on sampling, okay, because you cannot, the universe is too big, and then we can take a sample, but you can only sample the past, but you cannot change the past. It is too late. But what you like to change is the future. But today, you can't sample the future in a real sense. You could model the future, you could have a simulation, but you can't really sample the future. But what we like to change is the future. You cannot change the past. So then the idea is we say that that's why quality improvement is important, not statistical stability. And the focus has to be on improvement and not just on measurement. Many times people think I can measure something. Of course, measurement is important, but just because you can measure something doesn't mean you can improve. Improvement is a very, very different concept than measurement. So Deming then started saying, oh, statistics is like in sampling sense, he used the word enumerative. He says really focus has to be analytical. So you use the statistics, you use the past to develop the causation. So that's what science is all about. We do a lot of experiment, we can understand the causation. Once we can make the models, then I pretend my models are correct, and then I use all the engineering knowledge, all the equations to design something. I make the decisions, I act on the present, and then so that if my models are correct, hopefully I'll be able to change the future. How my ability to change the future depends upon how good my understanding of the system is. So he promoted, he says, focus of quality has to be based on analytical models and not based on statistical sampling ideas in statistics. So the basic idea is that if you have a process, you look at the output of the process, and today I have this statistical distribution. Focus is not to make sure that this distribution remains stable, because we don't want stability, we don't want control, we want change, and we want change for the better. Don't in any society, you don't want to be stuck in a certain way of thinking with certain processes, certain targets, and so on. The objective is to change this distribution. If you think high values are better, you want to change the skewness of the distribution. The objective is to change the process so that we can change the outcome. So the main ideas of quality control and their evolution over time has been is how to deal with variation. So it says we could ignore the variation, we could inspect the variation like we did more than 100 years ago. We could focus on cause and effect. That's what we have been articulating. We have to understand how to decompose variation, developing the function G as a function of all the inputs, and then do component of variations through design of experiment. Another idea has been, and we'll talk about the concept of robustness of manufactured products and processes, and then limitations of SPC was just focused on special causes. But most of the quality problems are not special. They are common. They are built in the system. And then people focus on feedback. And then we'll talk about limitations of feedback. We already hinted on. And then how we'll talk about mitigate quality through feed forward. So let me get a little bit idea of this. So if you have a system, there is always many unknowns. Yeah, all of us know there are known unknowns and unknown unknowns, all kinds of unknowns. Some of them we can control, some of them we cannot. So that's why output would be a variable, because I don't understand, I'm not measuring all the noise. So then the feedback means is that because you're not measuring them, you measure the output, and then if output is not what it is, then you give or change the input. Hopefully, you can try to hit the target. But you can see we said that there are a lot of limitations of this idea, because if I wait for the feedback, it is too late. So many people now talk about, how the brain functions. People say, no, we live in the future. Brain is always anticipating what is going to happen in the next microsecond and next second. If you really think about it, if you apply feedback, and if I throw a ball at you, you won't be able to catch it. You say, oh, I look at the location of the ball, and then here the ball is. Now I'm going to move my. You won't be able to catch it. You have to anticipate, predict where the ball will be next microsecond, and then you want to. So that is the idea that we can use in manufacturing. So you have a disturbance, don't focus on measuring output, but measure some disturbance. Some of these disturbance you will never know. So you could say, oh, there is still some limit for measuring the output. And then as disturbance is changing, then you are changing the input without disturbing the output. That's the basic idea. You can use, at least if you don't understand too much about the system and the noises, you can combine feed forward and feedback in. So we can then decompose disturbance in many different ways. So again, like I like to emphasize, you don't want to focus on inspection. People taught, I don't know how many billions of dollars were spent all over the world to teach people statistical process control. And now people say, oh, it has no meaning. So then focus on feedback, but we'll focus a little bit more about decompose the disturbance. Some of the disturbance we do understand, and we know how it affects the output, and then try to be proactive in the system. That's the basic idea. So another concept about disturbance, that we use the word noise, and this was promoted a lot by another quality expert, Dr. Taguchi. So he died about 10 years ago. He learned about these ideas at Indian Statistical Institute in Calcutta. So he was there in 1950s with Professor Mahalanobis, and he learned about design of experiments. Then he went back to Japan, and he started promoting some of these ideas. So he says, oh, there is all kinds of disturbances, like time is a compound noise factor, but then you could decompose disturbance into outer noises, they are outside the system. There is always a degradation of the system. There is a variation, like due to that processes are not perfect. So piece to piece variation. So he says, oh, rather than focusing on the variation as a cause, rather than try to eliminate the cause, you try to make a system that is robust against the cause. That even if variation is there, it is not transmitted to the output. That was his basic idea. That how to mitigate the variation of a manufacturing process or of product design so that it is not transmitted to the output. So I'll give you a little bit ideas. So like if I look at this picture, like any system, any product, any process is working at 100% level, whatever our metric is. And then it does degrade and everything will degrade. Degradation is related to the word reliability. and robustness. If something is very robust, that means that when there are noises, it doesn't degrade from 100% to say 60% or 40%. It doesn't degrade. And then if it degrades, then we have to bring it back to its ideal state. So that's like the notion of adjustment. Many times in system sense, we use the word, oh, how to sustain it, how to maintain it, or how resilient something is. The word resilience means is that it's able to recover very fast. I know it will degrade, something bad has happened, I got sick, but I can recover and go back to perfect health. So many times we talk about when we design manufacturing processes, three arts of engineering. So these are like in education, we talk about reading, writing, arithmetic, three arts. So these three arts are reliability, robustness, and resilience. It says anytime you design systems, processes, they should have these three R's. They should be able to do what we say they are doing, and if something bad happens, they're able to recover very, very fast. So the whole idea of improving the effectiveness of the system is trying to get rid of this red area. So you can see this idea of robustness that Dr. Taguchi promoted, it is very important part of biological systems. So how, as human beings, how is our robustness? And if you're not very robust, like if there is COVID virus, we will definitely get sick. So the question is how to improve design system so that we can focus on our immune system. Robustness is very similar to the idea of immunity. And there are all kinds of ways that we can learn how to design systems so that they are very, very robust. And this evolution has taken place over billions of years. And these ideas of robustness we can use in engineering systems, management systems, political systems. It doesn't really matter. The ideas are the same. It's like many countries, we say human beings are weak. We know people have greed and they do all kinds of crazy things. But how to develop even a political system so that the impact of human weakness, human error, human mistakes is very small on the system. Like we talk about in the United States, the notion of checks and balances. So you have three branches and they evaluate each other and they're trying to always make a adjustment. And that's a much better system. Resilience word, I think most of you in engineering understand, it's like something is deformed and can it recover? The same idea is in a system. It's a machine, degrades, can it recover very, very fast? So that's the idea of resilience. And you can make very simple models for the system where you have inputs, you have many outputs, there are many, many qualities. There are so many disturbances. Some of the disturbances, I use the word informative, means you have an idea that how this one will change this one. Some of the disturbances, either you don't even understand them. So if you don't understand them, there is no way you can measure them or control. And some, even if you understand them, you are not able to control. So you can see we can make a whole big matrix of all kinds of disturbances that we have in this. And every system is a part of a bigger environment. Then how to improve any one of these qualities. Improvement means is trying to hit the target. So that means reduce the bias from the target and then reduce the variability. So this idea was promoted by, I think many people knew about it, but Dr. Taguchi took a lead in promoting that, and he broadened the idea of quality engineering, not just in manufacturing, but more what he called as offline versus online. Offline means is quality is not just in manufacturing, it is in product design. And in manufacturing, you have process. and different components of the process. So this was his idea of systems design, then how to set the values of the parameter A, B, C, so that you can achieve the target. And these parameter values are so that the system is very, very robust. That was the basic idea. So the basic concept is that anytime you have a system, there are noise factors, there is an intent from the viewpoint of the customer, and then you have some ability to change the input, but then you want to change the input so that the effect of these noises on the response is very, very, very small. So that was the idea of robustness in manufacturing processes, in product design. So now I'll give you a little bit example. You could make a mathematical model. So you can see in the y is a function of the signal factors and the error that you have, which you don't understand, and the noises that you do understand, and then you have a target value. There will always be a variation because of this error. And then you want to minimize the quality loss. You want to integrate it over all values of noise. That means all values of the y. You could look at the expectation. You can see here we don't look at good and bad. Everything is, you could say, is defective. Any variation up to 10th decimal place, you could say, is causing some noise. And then the objective is to minimize this function. Then you could say, how can I minimize this function over all the control or the noise factors? This becomes a very complex process, especially in manufacturing, because people don't understand the mathematical models. That's why people have to do a lot of experiments. And then once you can develop the models, then you can keep using those ideas in the future. I think this is a very classic example. There, like Taguchi wrote in his book, like in Japan in 50s, they bought this product, this kiln to make tiles. And we manufactured it. This was the best product. And then you can see if I'm making tiles, you stack a lot of them, and then you are burning. So there'll be a lot of variation. Because of course, this will be very hot and this will be cool. So the dimensions will change. And there's nothing much you can do. You could just bake one tile at a time, but that's very, very expensive thing. So this noise is part of the system. There's nothing much you can do. The question is, but I can do something about how I design this product. So today, you can see if I look at the distribution of the tiles, outside tiles have a different size than the inside tiles. But then I can understand the process and I could change these factors so that my output variation. So that was the concept of robustness. Because you have a lot of possibilities. It's this amount of limestone, but you can change it. And you say, if I change it, maybe there is a lot of mathematics behind how you achieve robustness. We don't have the opportunity to cover all of that, but gives you a perspective of what robustness is trying to do. It says we can change the input so that the variance is not. So you can do an experiment, you can analyze the data, so we'll go fast over this, and then you can try to optimize it. You say, if today this was my manufacturing process, then what is the optimal setting? And then by optimizing it, how this distribution has changed to this distribution. This distribution has changed to this. So now you can see that even if you have specifications, both inside and outside, they're trying to meet your requirements. But that was the basic idea of robustness. These ideas of SPC were promoted to the concept of Six Sigma. And now you'll find is that even Six Sigma is no longer popular. You don't hear much about it. Company that promoted was General Electric, and a lot of people are having problems with General Electric. Their stock from $80 went today to $13. So it has same flaws what I talked about before. So you can see first thing, anybody that has a critical thinking, you say 6. Why 6? Why not 7 or 8 or 9 or 5? So it is very, very arbitrary. And focus was again on minimizing the effects and not focusing on fundamentally changing the system. So they had steps. They said, today we don't understand processes. These are my requirements, but I can improve the process so that I can be within the requirement. And once I can improve it, then I am done. But the idea is that these limits you must remove. Like remember we talked about specifications are barrier to improvement. They inhibit you. We always tease people. We say if you are a leader, you're a good leader, true leader, you don't need standards or specifications. If you're a leader, your job is to set standards for other people. Some people have. So always try to be a leader in manufacturing, where you don't focus on these national or international. You set the standard for whole society to meet, and these standards, of course, are dynamic. They're evolving over time. So focus has to be on continuous improvement, strategies, changing specifications, and so on. So briefly summarize like what we covered so far is we said, quality evolution over time. We have moved a lot from audit and inspection. Then we are moving a lot from statistical stability. All the control charts have no meaning. I think we should slowly eliminate them from textbook. If you look at quality control textbooks in 50s and 60s, half of the books will deal with inspection. And then in 70s and 80s, 70-80% deals with control chart. And you can see we understand the limitations. And now today, most of the philosophers and deep thinkers in quality, including Deming, towards the end of his life, this is the most important thing is the common cause. That means this is systemic variation, not the special cause. And Dr. Taguchi will say there's nothing like a special cause. If there's nothing like a special cause, means there is no control chart. Because control charts are capture the common. We'll then talk next about diagnostics and prognostics and feed forward. So that is what the trend is more and more in the future. So even the ideas, you can say feedback, I give you feedback, you can do diagnostic, what you tell me what is wrong. But the idea is, can you predict what will happen and then how to be proactive and make the changes? So this concept was promoted by Hippocrates. That's almost like we're talking about 2,400, 2,500 years back. And all the medical field is based on this book on prognostics, the book of prognostics. All the doctors in the United States have an oath to take based on this idea of prediction. If you are a patient, I take your blood pressure, I could do testing, and I could say, oh, you have a virus. What is my prognosis? What I think could happen, may happen to you next week, next month. But most important thing is not just to be able to predict, but what can I do to prevent that prediction from happening? What can I do to prevent it? So this is a very good idea. He says as medical people, we shouldn't do any harm. It is not just to fix the disease, but try to prevent it, if mitigate the disease. So he's focused a lot that doctors, we say even engineers and managers should take this oath of trying to do no harm. Google adopted this idea as a motto. do no harm as a principle to adapt. So let's expand on that again. So if you have a system, we say I have perfect prognostic. That means I truly understand Y as a function of A. If I truly understand it, this is very simple. Somebody says, oh, I have perfect knowledge. I could solve the inverse problem. So you tell me what Y you want, I'll tell you what A. But in real life, that is not true, because we talked about there is a lot of disturbance. There are so many things that we don't know. So the idea is there is this disturbance. This disturbance will make Y a random variable. That's what this is trying to say, that Y is something that you cannot predict. It's random because there is if you have a machine, you're monitoring the machine. Machine is supposed to degrade in a certain way, the way I designed it. It starts deviating, then I can make some adjustment to prevent that this path doesn't continue. Will move more towards this path. So that's the basic idea of doing prognostics, and then not just to predict, but also to do something different today, so that this red line is not followed tomorrow. That's the basic. So you see, this idea of prognostics we can use a lot now in engineering design of manufacturing processes, and so this I gave you on this presentation a lot of definitions. I always try to focus the meaning of the word and the evolution of the word over hundreds or thousands of years. And if you really understand the meaning of the word, then we can communicate with each other. If I use the word quality, I have one interpretation, but you have a very different interpretation. You'll find that very soon we'll be arguing with each other because we are not able to communicate. And that has been the biggest barrier in improving quality of manufactured things. So to understand, there's another person that we want to give credit to that had big impact on improving quality is Dr. Fisher, like all the statistical approaches, design of experiment. So his basic idea was, like we're saying, is this feedback is no good, but I understand the relationship between inputs and the outputs. And only way, and I say, I don't understand all the physics, chemistry, biology, psychology, to understand all these relationships. So if you don't understand it, like as a scientific approach, you do experiment and then use the data to infer the relationship. And then you use this relationship to do prognostics, to predict that as D changes slightly, I know what is going to happen to Y. So what sometimes in economics, we talk about that in medicine, leading indicator rather than a lagging indicator. Feedback is lagging, but you want to be leading. The reason I do a virus testing is I want to be a leading indicator, not after you're very sick, that is a lagging indicator. That's the idea. So Fisher did excellent work, and this has the biggest impact, like if you think in agriculture. More than 100 years ago, people never understood what to do. Like farmers in many countries still don't understand. But he said, oh, we can do experiment and we could tell you how much fertilizer to give, how much water to give, and so on. So that was his basic idea. So I have a couple of pictures just to expand on that. And you can see that there are a lot of ideas, like in engineering, in manufacturing processes, how we can apply this idea. Say, like if you have a car, of course, if there's a slope means the velocity will change. But you can measure the slope before and then take a control. Like in manufacturing plant, your focus should not be on the output temperature, but on looking at the temperature of the cold water. And as the cold water is changing temperature, you can increase the amount of steam so that your hot water is right on it. So this is the basic idea of a prognostic. There's a company called Apple. This is very popular. So Steve Jobs always said customers don't know what they want. So he was even going beyond quality because you're evolving, you're developing new products and people have no idea they need those products. Many products are based on that philosophy, like iPhone, iPad. So then one of the students at campus says she wants an boyfriend. He said, "Oh, what is an boyfriend?" This I comes from like, he said, an boyfriend is a boyfriend who knows my needs before I know I have them. So you have, that means that you're hitting at, somebody is able to anticipate what you need. So that is the idea that you want to promote in manufacturing. Not every disturbance, there will always be a residual disturbance. So there is an informative disturbance. And then you want to use informative disturbance to prevent things from happening. So now you can see that our technology is changing. So there are millions of disturbances. Before we never knew how to measure them. But now we have so many sensors, and sensors are becoming so cheap. In any one machine, we can put hundreds or thousands. Today, if you look at a car, there are so many sensors. Everything I can measure right away and then prevent it from happening. As anything is changing, they say that we can measure and monitor most of the physical, chemical, biological, even psychological, and then characteristics. The word characteristic is same as the word quality. And then we can change the output of it. So the traditional thinking we talked about was binary. So then we say that binary is no good. We could make it multi-state, or we could make it a continuous, or we could make it plus. These are some of the ideas of how to expand the notions of measurement of quality. So let me talk just 1 minute and then I can finish it. So it says we talk about a principle, then what are some of the principles, how to change it from a very chaotic system to something very streamlined in manufacturing. And there is a wisdom that we go, a lot of emphasis these days is on data analysis, but you understand what is the reason for data. And I can very briefly talk about, I used to talk about artists. So this Pablo Picasso once said, if you look at this woman, he said, this is not the truth. So he says, my art is a lie that reveals the truth. So you think about that. How can this thing, which is not true, can reveal the truth? If you look at calculus, for an example, they say delta x goes to 0. But what is 0? Physicists in quantum mechanics would say, what's the smallest number you can ever think of? So 0, we don't understand. Infinity, we don't understand. So I sometimes say calculus is a lie. It's not the truth, but it helps us understand still up to a point the universe. So those are many limits of science, and how today, because of all these sensors, we can integrate things like we talk about Internet of Things in the future. We do a lot of machine learning and artificial intelligence, deep learning. So maybe I can try to stop right now. I think I know we're running behind. So the basic idea is, in summary, is that you want to do less of design, test, redesign, retest, inspection. So you want to more focus on the output. I'll be happy to answer any questions. And then maybe last slide, I want to show you. Sometimes I say, oh, I'll answer questions. You see, I'm already done the damage. Isn't it too late to answer the question? So hopefully in the future, every person that is listening, like if I have a classroom, I can do facial recognition. As some of these links change, I know you're not happy with my statement or you have a question, I can answer it right away rather than wait for an hour to answer your question. Thank you very much. It's my pleasure and honor to make this presentation.
Thank you, Professor Kailash. It was a fantastic talk that you have given. To